Morning everybody, and welcome to the KARALIT 2.1 demo. The demo I'm going to show you today is related to the building flow app. So basically an app that we use to perform an external analysis of wind over a specific urban district. So let's start to create a new project on the folder demo that I have created here. And we call it Garibaldi because we are going to use Garibaldi Towers CAD. Let's choose a building flow app among the 6 apps that KARALIT offers today. Once you have created chosen the app, you are going to be requested to import the surfaces. In this case, this is the surface we are going to use. So it's an extract of the more complex, of course, environment of the Milano district. It's just related to the Garibaldi Towers. Once you import it, you will see that the geometry will be resized, will be immersed in the bounding box that will be automatically resized in order to position your CAD enough length upstream, downstream, in order to avoid the disturbances effect of the side of your domain. Of course, we have different options here in terms of volumes and things that I can explain a little bit later. Let's pass to the second tab, which is the meshing part. KARALIT uses an immersed boundary technology, so you don't need to spend manual time in order to prepare the mesh. You just basically need to select a few parameters in this tab. First of all, let's try for demo purposes to reduce our domain, maybe by sizing it to 1,500 meters in each direction and 500 in height. And then we can use maybe 50 meters length in each direction, so we have a mesh, an initial mesh like this one, for example. Or we can stretch a little bit on the X side if you want, in order to have stretching a little bit longer sides on the X direction. Then we can use, for example, resolution of the wall with a resolution in the outer layer. So the initial grid spacing will be refined up to the wall by choosing these parameters at 2 meters, 4 meters tangential. We can also increase in order to give a proper aspect ratio to the cell near the boundary. And basically, those will be the basic step that will allow us to generate a first tentative mesh. See? So we can position 5 meters from the ground, or we have the refined mesh like the one we have created. Of course, we can improve the situation by, for example, creating certain layers near the wall, so clustering a little bit more the resolution near the wall, and also in the intermediate layers. And we can repeat the process, the local grid refinement, like that. And we can, for example, choose that this will be enough for our first run. We pass to the fluid tab, where we set up the proper setup of the fluid in terms of turbulence simulation. We can choose ideal gas of state, the properties of the fluid, precondition, because we are going to have a low speed type of analysis. Then for the initial values, let's make this consideration. Let's suppose we want to consider, for example, a wind coming from northeast. Okay, so we are going to use the boundary condition tab, like this one, which is properly customized. So let's put, for example, wind coming from northeast, okay? And we select the proper speed of the wind, 10 meters per second. If you come back to the fluid tab, you will see that the components of the velocity will be automatically calculated by the systems, so we can initialize in a proper way the initial flow field. Of course, you can also have a more detailed analysis in terms of atmospheric boundary layer, where you can consider a proper roughness of your area. Either the wind is coming from calm sea, or is coming from a rural terrain, or from a urban area. You can specify a proper height to consider a proper roughness of your domain. Of course, the ground can be used in specifying a different way. In this case, let's suppose we don't want to consider boundary layer development on the ground. We can select the surfaces, which is in this case a single surface representing the full building. As no slip, we can monitor the forces on the building during the run. We don't have any volumes here because we didn't select upstream, but if we select volumes, we can use volumes to set up a specific boundary condition, like for example a forest area that we want to impose specific porosity models in the island, whatever. Then we pass to the last tab, which is the simulation. We choose the solver implicit. We can split the domain in more parts in order to profit of the parallel capability of the KARALIT CFD code, and basically we have completed the simulation. If we start, then we are going to have the log tab populated. There will be all the processes in the background that the solver will perform to manage the immersion of our geometry. So there will be the immersion process performed and progressing here. So there will be the processes used by the software to properly investigate the fluid cells, the solid cells, and capture all the intersections with the boundary and position the boundary in a proper way inside the domain. So in just a matter of few seconds, we will be able to start with the simulation. And you will see that the simulation will start here, and we could then monitor the convergence and all the aerodynamic forces along the STL that we have immersed. So now we will have the first iteration showing up in a matter of seconds, and this completed in a very efficient way a first analysis. Of course, we can, while the system is running and monitoring the forces along the wall, we can also show you that, for example, another way not to use KARALIT is to monitor and to visualize the proper pressure distribution along the walls and calculate the net pressure forces along the wall or specific parts of the wall. That can be very useful for civil engineers in case they want to transfer this information as boundary condition for a structural analysis calculation later on. Of course, the complexity of your urban environment can be any type. This is an example of the full Milan district I was talking about before. We have just concentrated in this example on the Garibaldi Towers here, but we have, the new Gaia Aulenti Square in Milano with a new skyscraper position here. This is the new square that's been studied also from the fluid dynamic point of view in order to understand the effect of the wind, of the pedestrian comfort area, pedestrian comfort issues related to the position of this tall skyscraper in the pre-existing urban district. And so this is much more complex environment that can be managed with the same facility, with the same usability as the example I was showing you a few seconds ago. So the system is running, has already performed the first 50 iteration, and we can, for example, use also the integrated visualizer to visualize the results. We can immediately see the speed and the velocity distribution on a certain position of the ground. Now we have 5 meters, 5 meters for the ground. Of course, we can as well monitor the pressure distribution along. So we will have, of course, the winds coming from northeast impacting directly this side of the facade. We can change the section and see what's happening in the other section. We can go back to the velocity, and we will definitely see another vision of the results. So this is pretty easy, and we can do a first visualization of our results here, and of course you can perform a more detailed visualization using external post-process like TechPlot and CytoParaView that will allow you to perform a more detailed quantitative analysis also. If you are interested in force distribution along specific walls or whatever you like. So that's basically concluding my demo of today. I thank you for your attention, and for any additional details or clarification or information you might need, please contact us at sales@karalit.com, and we'll be very happy to give you all any additional information. Thank you very much. Bye-bye.